All right. Let's talk about this LD50 now. So I told you that these safety data sheets can get very confusing because pretty much everything sounds dangerous. Why is that and what's going on? So some quick toxicology terms. Exposure is contact with a chemical substance anytime you get in contact. So the shampoo you're using or the toothpaste or whatever, those are exposures to chemicals. Um, and then there's a dose, right? You can brush your teeth and not die, but it turns out you've probably heard that fluoride is toxic at a certain level. So a dose is a specific measure of exposure, and we express that as a amount of chemical per kilogram of body weight. And then there's this other thing called a lethal dose, which I'll get into, but that's LD50 is a lethal dose 50, and it's the dose that would kill 50% of of a organism. And that, as with dose, is milligrams of the chemical per kilogram of body weight. So let's first talk about why that is. Why milligram per kilogram? Well, here's a Nexium ad. Nexium helps with heartburn. And here are some poor heartburn sufferers. And it would make sense that this young lady would need more medicine than this little baby to have an effect on her, right? That if you gave 2.5 milligrams of this substance to her, she has the body mass to dilute that and it might not help her heartburn. Whereas if you gave 20 milligrams of this chemical to this baby, that might do some real damage to it. So body weight will determine how much of a dose you need. And so that's why doses are considered in milligrams per kilogram. And here are some LD50, so things that will kill you are half the population, the dose that's required. So the dose tends to be what makes something hazardous. Like I said, fluoride will kill you, but not what you put on your toothbrush every morning, obviously, because you do it every morning. So water will kill you if you're a 160-pound human and you have 6 liters of water in you. If you drink 6 liters of water, that will kill you. That's interesting, but I'm going to believe this because here's my source. So that breaks down to 82,800 milligrams per kilogram of body weight. And then alcohol, half a liter, so about of pure alcohol will kill you, and that turns out to be 7,000 milligrams per kilogram. A cup of salt will kill you, or half of the humans of 160 pounds. 2 teaspoons of acetaminophen, so that's pure acetaminophen. This is Tylenol. What you take in the tablets is often has some other things in it, like chalky stuff that to make it mix well. So anyway, 2 teaspoons of acetaminophen, Tylenol will kill you. That's 150 mg. So the point here being that as things get more and more dangerous, right? A pinch of cyanide will kill a 160-pound human. A drop of nicotine, this is what's in cigarettes, will kill it. So if you had pure nicotine, obviously cigarettes aren't pure nicotine. Only a drop would be needed to kill you. This LD50, as you can see, the magnitude of the number is going down as the thing is getting more and more dangerous. And that's sort of the point, right? Dioxin, one of the more toxic things we know, 0.001 milligrams per kilogram will kill you. Just a dust grain worth exposure will kill a 160-pound human. So anything can kill you. It's just the dose that you need. So water can kill you. It's just you need to drink 6 liters of it if you're a 160-pound human. All right. So that's one thing to notice is, right, that dose determines poison. That's why sea sand can sound so toxic, is because if given enough sea sand, it can kill you. But the reality is this LD50 will give you a nice number. So you really know whether or not this thing is that dangerous. Obviously, water is not dangerous, it has a big LD50. Obviously, dioxin is, it has a very small number. So to further exemplify this, let's say we're trying to kill predators. All of a sudden, there's some predators on Earth, and we need to get rid of them. And we capture some, and we're trying to figure out how to get rid of them. And someone says, hey, I bet Mountain Dew will kill predators. And we're like, okay, well, let's try some Mountain Dew. So we give predators some Mountain Dew. Now, a couple things here to notice. One is we don't have all day to figure out how many predators we can kill. So what we do is we multiply by 10 every time how much we're going to give it when we do this testing. Because look, you can have something that kills at a 0.001 level and something that needs thousands of milligrams. So to sort of cover that quickly, the doses we give, we multiply by 10 every time. So we expose 10 predators to 0.01 mgs of Mountain Dew per kilogram, and it turns out none of them die. Right? We're like, oh, this doesn't look good. Then we give them, the next group, 10 times as much, 0.1 milligrams, and we kill one. And we're like, oh, but maybe he just had heart trouble. We don't know. So then we have another group of 10 predators, and we give them 10 times as much, 1 milligram per kilogram, and it kills 3 of them. Now we're starting to see a trend like, oh, wait a minute, this is killing them, I think. So we multiply that by 10, and we kill 5 of them, and we multiply that by 10, and we kill 7. Multiply that by 10, and we kill 10. And then we can multiply that by 10 and kill 10 more, right? And we can multiply that by 10 and probably kill 10 more, right? So this sort of maxes out. There's a point where it's killing everything, and there's a point where nothing's happening. And so this makes for a very nice graph. And here's the nice graph. So when we had 0, which is down here, let me try this. All right, so down here we have 0. Nothing happened. 0.01, nothing happened, right? When we had 0.01 milligrams per kilogram, nothing died. But the first instance when something was affected was at 0.1. So that's the first death we had, and then we can graph the deaths that we have per dose, and we get what's called a sigmoid curve, or if you look at this, it's going to sort of be an S shape. And it maxes out, right? There's a point where it doesn't matter how much, if we did 100,000, that would also kill 100% or all 10 that we had. So we don't have to keep going after we max out, and there's a minimum, and we don't have to get any lower than 0.01 because we know that's not going to have an effect. And from this graph, hopefully you can read what the 50% mark is, right? So here's 5. So this would be the LD50. So my hope is you can use this graph to find an LD50 and understand that there's a plateau, right? There's a point where it doesn't matter how much more you give them, they're all going to die anyway. And that there's a point where everything gets started. That's sort of the point of all this. That's why I decided to do this. So that is safety. I hope you enjoyed it. We are going to discard my annotations, and that's that.